Hey everybody, Fade here, and today we're going to be going over the limit definition of the derivative. So let's get started. Okay, so let's say we have some function here where the points P and Q belong on this particular function here. Okay, and we want to find at least approximate the secant line of this function by finding its slope, you know, this particular secant line. So in order to find the slope of this particular secant line here, we need two coordinate pairs, right? Because we know that the formula to find the slope of any line here is, right, the slope, which could be denoted as m, equals to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So in this case, we need to find two coordinate pairs. So think about this here. One of the two coordinate pairs must correspond to the point P. Then the second coordinate pair must correspond to the point Q. And both of these coordinate pairs must, of course, belong on that secant line. Okay, so if we sort of think about it here, the x coordinate for the coordinate pair that corresponds to point P here could be denoted as x. And then the x coordinate for the coordinate pair that corresponds to point Q here could be denoted denoted as x plus delta x, where the distance between x and x plus delta x is, of course, delta x. And then the y coordinate here, so if the y coordinate for the coordinate pair that corresponds to point P here could be, denoted as f of x, and then the y coordinate that, for the coordinate pair that corresponds to corresponds to point Q could be denoted as f of x plus delta x. So now think about this here. We have our two coordinate pairs here. So the first one is x comma f of x, and then the second one is x plus delta x comma f of x plus delta x. Sorry, I was having a tough time pronouncing, things. Sorry. But anyways, so now we can apply the slope formula here. So we could, or we could just assign this to x sub 1, this to y sub 1, this to x sub 2, this to y sub 2, and then apply that slope formula to approximate our secant line. So then m will equal to y sub 2, which is f of x plus delta x, minus y sub 1, which is f of x, then over x sub 2, which is x plus delta x, minus our x sub 1, which is x. And then our x's in the denominator will cancel, leaving us with the approximated secant line of f of x plus delta x minus f of x over delta x. So this will give us that approximated secant line. So now using this, how could we approximate the tangent line? Specifically, we found the slope of the secant line here, which helps us approximate that secant line. Well, how can we sort of find the slope of the tangent line using this approximator, or the slope of this secant line here? So in order to do that, well, we need to sort of figure out, sort of what will happen when the points P and Q get closer to each other, and how that will impact the distance, specifically the value of delta x, right? So as P and Q get closer to each other, well, the value of delta x will approach 0, right? Because delta x is a distance, right? Meaning that when P and Q get closer to each other, specifically that slope of that secant line, as those points P and Q get closer to each other, that means that delta x is approaching 0, giving us that slope of the tangent line. So we could, of course, delta x is approaching 0. We could, put that as a limit here. The limit as delta x approaches 0, then of the secant line, or sorry, this slope of the secant line, which, approximates our secant line of x plus delta x minus f of x over delta x, gives us the slope of our tangent line. So you sort of have to think about it here, right? Delta x is a distance. As P and Q, the points P and Q get closer to each other, what is happening to the value of delta x? And of course, it is approaching 0. So as this, P and Q, right, we found, with those points P and Q, our, approximated secant line, just sort of seeing as P and Q get closer to each other, delta x has to approach 0, and how as delta x approaches 0 of that secant line, that approximated secant line, we get our tangent line. And of course, when we find the derivative of a particular function, we are finding the slope of its tangent line. So that's just sort of, looking at it from a different perspective here in terms of limits, how we use that secant line to find our tangent line. So now with this, of course, limit definition of the derivative, which is, right here, with this definition, then, people have, you can then, of course, prove the power rule, which is nx to the power n minus 1. And that all comes from this limit definition. We're going to talk more about the power rule. Maybe you've heard of the power rule, maybe you haven't heard of the power rule. Really depends. But that all comes from this limit definition. So now, you can sort of conclude here is that whenever you are finding the derivative of a particular function, you are basically evaluating the limit at the same time. Of course, with the whole limit notation, that all is not really incorporated in derivatives, but you just sort of have to think about it. You are basically evaluating a limit when you are finding the derivative of a particular function. So, sort of cool to think about here. This is just, really, cool. You know, this is just sort of really nice to visualize here. And I hope, you guys also, think of this, the same way here. Okay, so I'll see you guys in the next one.